Okay, so like I was just saying, this is the Unit 6 review for electrostatics for honors physics. And if you're watching this on YouTube, then hopefully it's helpful to you. If you're watching live, then hopefully you understand that the point of this is that you can ask me questions as we go. And you can ask either via the Twitch chat or you can use the Remind app, and I will respond either way. So my phone is over that direction, so if I glance over there, that's just me looking at my phone. The Twitch, though, is way over there on my monitor, and so I'm going to be looking over there once in a while. And so if I don't see your question right away, just be patient. I'll look over there now and then. So this is Unit 6, electrostatics. A couple things to keep in mind as you take this test, or as you get ready for this test. First of all, make sure that you are just comfortable with the Bohr model of the atom. Okay, so I'm just going to put, I guess, atomic structure. Atomic. Sure. Okay, so protons, neutrons, electrons, where everything is located. The charges, so protons are positive, neutrons are neutral, and electrons are negative. Make sure protons and neutrons are in the nucleus in the center. They cannot move, at least they can't leave the atom. And electrons are the things swirling around the outside. Typically, you're going to see what's called the Bohr model. You don't need to worry about the name at this point, but it's the one that looks like the planets. Just be familiar with that is all I could say. Yeah, that's it. So the basic understanding of how electricity works is understanding that the electrons are able to leave the atom and they can move around from atom to atom. Okay, the next thing is you want to understand, how do I say this? The name is not super important, but I'm going to write it down anyway. Conservation of charge. Conservation of charge. Now I understand why Khan Academy always says what they're writing. So conservation of charge just means that charge cannot be created or destroyed. It basically is transferred from one object to another. In other words, the electrons exist. They're not like magical things. And if something becomes negative, that means something else had to become positive. The electrons had to jump from one thing to the other thing. And so there's a conservation of charge, meaning that however many total charges you started out with at the beginning, that's how many you're going to have at the end. Again, it just has to do with like if you charge something, then something else also gets charged because of that typically. All right. Make sure you understand how to do the balloons. The questions such as, so anyway, I'll get to that. So just looking at the review, again, briefly like reviewing this, this first part is just so that you're familiar with how to deal with scientific notation. I'll deal with that in a second in the calculator. The second part is, I gotta move my phone. Here's the question about the atom. Again, if you're just not sure, check the key. I'm not going to draw that for you, but suffice it to say that these protons should be in the center, in the middle, in the nucleus. The neutrons should be in the nucleus. And you should have, I'll pause for effect, 3 electrons to balance out the 3 protons, because these are positive, these are negative, and it has to be neutral. All right. So, question 10, in a conductor, they can move around really easily. In an insulator, they're stuck wherever they are. They can't move through it. 2 types of objects attract each other. Okay, so again, just be aware that a charged object of any kind, positive or negative, will attract a neutral object, and opposites attract. So a positive and a negative will attract each other. Now, what repels? Well, like charges, 2 negatives or 2 positives will repel each other. What does nothing? 2 neutrals, pretty much almost everything. Okay, so the 6 combinations, I'm pretty sure I just mentioned all of them. So number 12 is that conservation of charge. And so now we get to the balloons. I'm not going to answer this question right now. Well, I should say number 14 is the balloons. I'm not going to answer this question on the live stream. that is just something you need to figure out. The only thing I will say is make sure you write these things down. So like if x is negatively charged, you should make a note, well, x is negative. Okay, I guess I'm going to kind of partly solve this. So we want to know what z is. X is not near z, so we need to, but y is near z. Y is interacting with z. So we need to figure out what y is first. And so what I recommend you do every single time is you've got all these possibilities for y. This could be any of those, okay? And just write them all down, even if you know already that they're not it, just because you get in that habit. It's like using the turn signal, even when nobody's around. You should still do it just to stay in the habit, okay? And you're gonna eliminate things. So you know if x is negative and it attracts the y, because over here it's attracting each other, then you know that if x is negative, then y could be positive. And so you're like, okay, I'll make a little note that could be positive, but it also could be neutral because it could attract the neutral. But you also know that it cannot be negative because it would repel. And then you go from there. Well, okay. And then you have to, now we can figure out, we know that y could be positive and it could be neutral. So now for z, you have the same possibilities. I guess I'm doing this problem. Positive, negative, or neutral. Positive, neutral, or negative. And so we have to explore all the possibilities. If, and we don't know which it is, so if y is positive and we know that they attract each other, then can z be positive? No. Okay, we're not going to completely ignore it yet because, well, anyway, we'll see. If y is positive, could z be neutral? Yes, it could, because they're attracting. It would attract. If y is positive, could z be negative? Well, it's attracting, and that's a possibility, yes. So now we've fully explored that one. Now we need to look at the other possibility, is if y is neutral. So if y is neutral, would that attract a positive balloon? Yes, it would. So that is a possibility now that z is positive. Would it attract a neutral? No, but we've already got that possibility down, and technically we could probably stop here because we already figured out that z could be any of these things. But let's just kind of game this out all the way through. Could z be negative? Yes, it could, because a negative would be attracted by a neutral. And so the answer is z could be anything. Z could be positive, it could be neutral, or it could be negative. We just don't know. It's not going to be all of them at the same time. It's just going to be one of them. We just don't know what it is. All right. So anyway, make sure you can do those problems. You'll see I just did this one, but I think there was a couple questions on practices earlier that are like this. And the Mind on Physics, there's a Mind on Physics. If you haven't done that one, do it. There's one that just deals with these balloons over and over again ad nauseum. And you know how Mind on Physics is. You want to throw it out the window sometimes. All right. So looking at my little balloons, how charged objects attract neutral objects. So I'm just going to write a word here, and it's going to be polarization. Polarization. That is how a charged object will attract a neutral object. Okay, think of the balloon and wall simulation. All right, that's what you want to think about. Balloon, 2 L's, wall sim. Okay, so the one we did where you, if you haven't done it, make sure you do it. The one where you bring a charged balloon, you rub it on the sweater, and then you bring it up against the wall, and you can see the electrons moving. That's polarization. Basically, the object stays neutral altogether. Like if you were to count the individual positives and negatives, they would still add up to be like basically equal. But one area is more positive than the other area, and so the balloon is attracted to that one area. That's polarization. All right, not seeing any questions yet. So moving along. That's essentially the first part of the unit. There were 3 parts, and that's electrostatics in a nutshell. So just again, what is charge? How does it work? And then you're good. All right. So part 2. Let's just switch colors just for fun. How about orange? Is going to involve the electric fields. Okay, so now we get into a little bit of math. What you really want to do is, how do I say this? Is, okay, here, I'm just gonna write this. Diagrams of interacting charges. Interacting charges. And you've seen a few of these if you've done the practices and whatnot. Question 24 of the review is one just like that. And you'll see different varieties of these. You saw them on the quiz. You saw it on different places. And this is definitely something you're going to need to understand. Okay, what is going on here? Can you rank these in order from strongest to weakest, for example? So in other words, okay, good. It's very clear on my screen. So you have a negative charge here. You have a +4 positive charge here. You have a positive charge here and a +8 charge here. I don't know why I can see it better on my monitor. You have a positive charge here and a -2 and a positive charge here and assuming +12. It's implied 12 positive. So can you rank these in order from greatest to least? And if you don't want spoilers, I would skip this part because I'm about to answer it, although it is on the review key. But the thing to keep in mind is there's two factors that affect the force that charges will feel when brought near other charges. And those factors are the amount of charge, Q, and the distance, okay, or the radius, however you want to say it. Okay, those two factors are the things that affect the charge. And I'm sorry, it should say it affects the force felt by the charges. And the charge, the Q, is a direct relationship, and the distance is the inverse square. So what you have to understand is, let's say, okay, this is a +4 charge. So compared to each other, it's going to feel 4 times the force, okay, because you've got a +4 charge. That's going to be our charge. Then, and a little confusion came up in class. The distance and the charge in these situations are completely independent of each other. One is, in this situation, the charge is what the charge is, +4 in this case, and the distance is just a set distance. Like in the scenario, we basically just said, okay, this is going to be 2 units apart. It's not 2 units apart because of the charge. It's just 2 units apart. End of story. So in this situation, if it's 2 units apart and it's +4 charge, what's the force? So you just look at it independently. I'm done with the charge. I said, okay, because of the charge, it's going to feel 4 times the force. But now, separately, I look at the distance. And in this case, the distance is 2 units apart. So because the distance is 2 units, I have to do the inverse square. So let me just take my orange and I'm going to sort of, for the distance, it's actually a 1 over distance squared relationship. That's the inverse square. So what I'm going to do is I'm going to take 1 over 2 squared and I'm going to say, well, that's 1 over 4. And so altogether, this thing feels a 4 times 1/4 multiplier of the force. So the total amount of force it's going to feel is just 1 unit of force, because we're kind of dealing in abstracts here. Another example, and then I will let you look at the key. I'll let you do the rest and figure out the key. I think I'm going to skip to C because we got the negative, and it doesn't say anything about negative or positive. It doesn't say anything about direction. It just wants the amount of force. So in this case, the amount of charge is, well, it's a 2, and again, it's negative, yeah, but it's two negatives, and so we're just kind of again, ignore the negatives in this case. If it's asking you to compare the amount of force felt, unless it's asking for a direction, which it'll be very clear if it is, just ignore the negatives. So it feels 2 times the amount of force because of the charge, and the distance is only 1 unit away. All right, so I'm going to take the inverse square of that. 1 over 1 squared, well, that's just 1 over 1. And so the total amount of force it's going to feel is 2 times the amount of force, okay, of the original It's two times the unit of force. So based on these two, you could do the rest of them yourself and check the key when you're done. But based off of these two, I'm going to say that letter C feels more force than letter A. All right? It feels, in fact, twice as much force as situation A. Because well, you just saw why. Okay? All right, not seeing any questions. Double check. All right. If you do have questions and they come up on this, especially, see me tomorrow, send me a message, or I guess not tomorrow, but just send me a message, let me know. Come in early Friday. And so that's that. Now, all right. Kind of talked about this when I was talking about, when I was doing that one, but make sure you are very, very familiar with, lost my orange, with the relationship of charge to force. So, relationship of charge and the electrical force. Okay, that's the direct relationship. So that's a P. So I'm just going to put direct. Okay, so as charge goes up, force goes up, electrical force goes up. Charge goes down, electrical force goes down. Just think about those balloons that I had hanging in the classroom. If I charged them up to the max, they had the greatest amount of force, and so they're pushed the farthest apart. When the charge started leaving the balloons, and just because of the moisture in the air, they started coming together, and so that's because the force between them was weakening. Also, know the relationship of distance, or R, if you remember that first thing, and I'm just going to stick with D because I just want to be consistent. So this is the inverse square. Okay. So example, or rather, just to see the pattern, and I did this on the board, but this is probably going to be a good reminder. Is if I have a little thing just comparing the distance and the electrical force, right? If I do 2 times the distance, I'm going to feel the inverse square of that. So I'm going to feel 1/4 the force. So I take the inverse of 2 and I square it. If I triple the distance, I'm going to feel 1/9 the force. If I quadruple, I'm going to feel 1/16 the force. Okay, and if I go the other way, let's say I cut the distance in half. Well, the inverse square of that will be 4. I inverse it and I square it. If I cut the distance by 1/3, I'm going to feel 9 times the force, and so on. Okay, so 1/5 would be 25 times the force. So if I take the distance and I cut it in half, is what I'm talking about, then I'm going to feel 4 times the force. That's inverse square, that relationship. So remember that. Okay, be able to apply it to different situations. And why is that? Well, it has to do with that formula. And the formula, I'll write it in blue. The formula for the force, electrical force is, so electrical force is, this is going to be K times Q1 times Q2 divided by the distance squared, or R squared if you want to use that version. It's the same exact thing. It depends on who you ask. And so you can see how the distance is squared. It's on the bottom, it's inverse and squared, and the Q's are just multiplied on top. And the big constant there, the constant that, well, I mean, by its name never changes, is K. So K is equal to 9 times 10 to the 9th Newton meters squared per Coulomb squared. Okay, so that is a constant. It never ever changes. That is the charge constant. So write that down. You don't, on your note card, you don't want to have to sit there and try to remember 9E9. Okay, just one less thing to remember. One less thing to have to remember. It's not bad if you remember it, of course, but since you had the opportunity, I'm not gonna. Yeah, I just think you should write it down along with the formula. So make sure that you can solve for any variable there. All right. So I guarantee you're going to see a question that gives you the electrical force. It gives you one or two, both of the charges, and you're going to have to find out how far apart they are. Okay. So, I mean, rearrange that formula now. Get ready for it. Okay. Just be ready to solve for anything. Or you're going to get the electrical force, and you're going to get the distance, and you're going to get one of the charges, and you're going to have to solve for the other charge. I guarantee you. All right. So, all right. Good. And the last thing for this is electric field lines. And so just be ready to have to draw it or identify if it's correct or not, and sort of like on the quiz. But the bottom line is this. If you have a, that's not showing up. It's kind of showing up, but I'm not just going to throw that away. How about if I use, doesn't matter, I'll just use the pencil. So if I have a positive charge and let's say a negative charge, then, well, what's going to happen? Always go away from positives and toward the negatives. And so you're going to sort of, as you draw this, you can kind of just let yourself feel what's happening. The lines are going to get pulled toward the negative. It's going to go away from the positive. Okay, it comes away from the positive, but you're going to feel it getting pulled toward the negative. Like I said, if you just sort of imagine that happening to you, you could kind of draw these lines. All right, so it's going to get pushed away from the positive, but you could sort of just feel that negative pulling you back. Okay, and that's how you draw these things. All right, draw away, and it gets pulled back to the other side. And just fill the space up. You don't, you can see I didn't draw very many. It's going to be pretty evenly spaced though, so you might have to do one of these things where it just sort of goes off into the distance, and maybe it just comes back from a distance, and it just sort of represents how this works. So I draw that again, and it goes beyond the reach of the page. That comes out from the page, from the paper. But again, just sort of practice it once or twice. Maybe put 3 in there. Like maybe you've got a positive and a negative, and let's just say, well, you know what, this is 1 by itself. So I'm going to just put a little box around that just to keep that little world separate. I don't know, let's say you've got 3 positives. All right, what's going to happen with those? Well, I mean, I kind of limited myself with the room here, but it's the same thing. It's going to go away from the positives every single time, and they're never going to overlap. Okay, never ever overlap them. They don't cross each other. They just get pushed away, gets pushed away, and just sort of be the line. Getting a little too like Bob Rossi here, but just be the line. Feel what's going to happen. It's going to get pushed away by the positives, away from positives, and toward the negatives. Okay, and if you just remember that, then you'll be fine. Okay, it doesn't have to be art. It just has to show 2 things. It has to show that it's away from the positives toward the negatives. That's one thing. And the other thing it has to show is that the lines never actually cross each other. Okay, that's the 2 things. So away from positives toward the negatives, and the lines never cross. That's it. I'd write it down, but I don't feel like it. Hopefully you're listening, because that's a lot to write down. All right. No questions. Good. This is just a review, right? And we're almost done. Because I'm not doing the math. I really don't want to do the math. I feel like it would just be... I don't know if that's going to be the weak point right now. All right. If you think I should do the math, go ahead and just say do a math, and I'll do a math. Okay. Or maybe I'll do one for gravity. But if you wanted to specify math, gravity, or electrical, or if you don't care, then I'll probably do one for gravity. How about I do one for gravity? But if you want one for electrical, I'll do an electrical example here. Probably like number 22. No, 20. Oh, hey, okay, 22 actually reminds me. So there is another equation. And that is Q is equal to NE. Okay, and all this is saying is how much charge an object has is equal to the amount of electrons that the thing has times the charge of one electron. And that charge of one electron is another constant, and it is negative 1.60 times 10 to the negative 19th Coulomb. Okay, so that's another couple things to definitely have on your note card for Friday, is that equation and that constant. Okay, again, this is the charge of one little itty bitty tiny, like not even like beyond microscopic electron. Multiply that by the number of electrons you have, and that's how much charge you've got. Questions might ask directly, how much charge does an object with 50 trillion electrons have? Or the question might be something like, how many electrons does an object need to gain in order to have a charge of 0.00075 coulombs? Okay, that's the kind of stuff you might see. In fact, like I said, what was that, question 22? Was in 22 and 23? Yeah, we both use that equation. Okay, so you can see question 22, it's asking for how much charge. It's asking for Q, and it gives you right here, this is N. Okay, and you just have to solve for Q. Multiply N times the charge constant the charge of an electron. How many electrons? So in other words, N does it take for an object to gain this much charge? So this right here is Q. You have to solve for N. That's okay. So if you know what the variables are, it'll make it easier to solve it. All right, still no excuse me, no questions is what I'm saying. Okay, so that is the second part of the unit. The third part of the unit, let's do this in, well, this seems like a different variety of purple. This is going to be gravity. All right, so in fact, I'm going to write right here, gravity. I kind of wish I didn't, because that's barely a word, but it works. All right, so gravity. First of all, keep in mind that all objects have gravity. Anything with mass. Mass causes gravity. All right, we could get into like warping space-time, but let's not for this test. Just remember, mass causes gravity. If you have mass, something has mass, you're going to have a gravitational field. You're going to attract the objects around you. That attraction is very, very weak, however, so just keep that in mind. It's a very weak force. It takes a lot of mass to have like a noticeable gravity. That's why we feel the Earth, but we don't feel like anything else on the Earth, like people or buildings or anything like that pulling on us. It's just very weak. The sun, the moon, all those things have gravity because that we can kind of feel and notice because of the mass involved. So you might be like, what do you mean the moon? We can feel that? No, you can't feel it, but I mean the tides are caused because of the gravitational pull of the moon. So I know we live in Illinois, but tides exist, and that's caused by the moon. So like before, like with the other one, make sure you understand with like electricity, the relationship. My handwriting is not getting better. Between. So mass and the force of gravity. Okay. And that's going to be, again, a direct relationship. So as mass increases, gravity increases. The force of gravity increases. Also, and I'm trying to write this one, relationship, that's almost legible, between. Now, the other thing is, again, distance and the force of gravity. This, again, is going to be your inverse square. So, again, if you look back at the other thing, it's the same exact thing. If it's just like this one. So instead of electrical force, it'll be a gravitational force. Okay, it's the same pattern. Okay, and the reason for that is our lovely equation that looks just like the other one, but same variables, different, not the same variables, but it looks so similar. The same arrangement of the variables. This is going to be a capital G, not to be confused with 9.8. So this is not lowercase g. The first mass times the second mass divided by the distance squared. Okay, and so that is our final equation of the unit, and capital G is a gravitational constant. This is constant for everything. It's not just on Earth. It's just asteroids, planets, whatever you want. And this one is 6.67 times 10 to the negative 11th Newton meters squared per kilograms squared. I did the color scheme wrong. Well, oh well, it was supposed to be in red just like the others, but I'll put a red cloud around it. So that is G. I'm not going to sweat it too much, but I'm going to do that because I feel bad. Okay, so that's our, make sure again, just like before, you can solve for any variable. You might get asked, what is the distance between two asteroids or the planets or whatever, the Earth and the Moon. You might get, have to ask to find out the mass of something, if you know the mass of the other thing and you know the distance and you know the gravity, force of gravity. So just be ready for all that. And finally, are we good? I want to show you one math question because mostly I want to revisit how to put things into the calculator correctly. So let's pick a question. Let me get rid of my colorful thing there. I'm going to pick one at random, not random so much, one that looks good. Only so many I could pick from. So I'm going to pick number 30. All right. So the Earth, and it gives you the mass of the Earth, and it gives you the distance between how many meters from the sun, okay, and it tells you the mass of the sun, the estimated mass of the sun. What we need to do is find the gravitational force between the sun and the Earth. So it's kind of a softball question, honestly, because we don't have to rearrange for any variables, but that's okay for this review. Just there's other questions on the practices if you want to practice that. So anyway, the Earth. So this is, we'll just call this pencil breaking M1. This is going to be your distance, and this will be our M2. And we need to find the FG. Okay, so we're going to do that. And so I'm going to use my little equation here. FG is equal to capital G times M1 times M2 divided by the distance squared. Then I will plug in the numbers. Okay, I don't have to rearrange for anything. So this is, like I said, very softball question. Remember, okay, so a couple things. I'm just going to, you know what? I'm going to pause here and go back to this thing. Okay, it's very pretty and everything with all the colors. I really like it. But I need to point something out to you just to remember this square. Okay, remember the square. If you have to solve for distance, just for random example, okay, you got to remember to deal with the square. So like if I were to solve for distance, I would multiply, I need to get distance by itself, so I would multiply both sides by d squared. So it would be d squared times fg is equal to gmm. And then to get d squared by itself, I would have to divide both sides by the force of gravity. So it would end up being, in the end, something like this. D is equal to G, capital G, times M1 times M2 divided by FG. But because there was that square there, I have to make sure I take the square root of that. All right, so that is just one instance where you have to remember the square. But almost that's a little too easy to remember the square in that situation. The harder part is going to be when you're like, so for example, putting it into your calculator and you've got all these other numbers there and you just forget the square. So I don't know how to, like, just maybe like, I don't know, highlight the little square. I don't have a highlighter on me, but maybe highlight that on your equation sheet. Whatever works for you, just don't forget it. So this is going to be G, which is, I'm going to put parentheses here, but I'm going to show you how to put it in the calculator, how I'm going to put it in the calculator. So 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared times m1, these are lots and lots of numbers, 5.98 times, however, do this because it's so much more likely you're going to make a mistake if you don't just organize it, write it down, and see it, visualize it, okay? Times m2, so that is the mass of the sun, 2, and you can see we have fewer significant digits, which kind of means we're a little like less, it's just a little less precise than the mass of the Earth. Times 10 to the 30th kilograms. All that divided by the distance squared. There it is, 1.49 times 10 to the 11th meters squared. All right, so there that is. And watch how the units cancel out. So I'm going to have a meter squared. So that meter squared will cancel out with that meter square up there. This kilogram times a kilogram is going to cancel out with this kilogram squared there. We are going to be left with newtons, which is good because we want to find the force between them. Now, what I really want to show you is how to put that in the calculator. So let's see if I can do this. Oh, I can. Look at that. All right. Except I can't see it. All right. Well, let's try this. So what I'm going to do is just, again, with the parentheses, 6.67, and then I'm going to use my E and make sure it's a capital E. On my calculator, it's not that. That's a letter E. It's a different E. It's this one. So be familiar with the calculator you're going to use for this test. That's all I could tell you. Hopefully you already are. So that's where I got the E from. And I'm going to do that. I'm going to end up close the parentheses. Oh, wait, no, I can't. I need to put my, like, what is it to? It is to the negative 11th. Okay, wait, something happened. Negative 11th. Okay, delete, just to make it clean. So that's how I do that. Okay, and then multiply that by 5.98 E, so times 10 to the 24th. All right, and multiply that times the mass of the sun, 2 times 10, or E, to the 30th. Okay, so I've got my top thing done. Now, if you really want to be redundant, you could put parentheses around the whole thing, beginning to end. It doesn't really matter because we're going to get the order of operations. That's how it works. But I am definitely going to put a parenthesis here, and if you want to put 2 again, just in case you can, but I don't think it's completely necessary. The distance, and I know it's right there and printed, but I also wrote it, so I'm very proud of my work. I want to make sure it's there. 1.49 times 10 to the 11th is the distance, and square it. Square it. Okay, now the question is, where do you put the square? Put it on the outside of the parentheses for that one. You want to square the entire thing, all right? So make sure that you get the same answers as what's on the key, and hopefully that's what it is. 3.59 times 10 to the 22nd is going to be the answer, except a little side tidbit, I'm not looking for it, but since we only have the one digit here, we cannot claim any more precision than we have. I will for now accept like 3.6 times 10 to the 22nd, but realistically, because of the precision involved here, the actual answer, you know what, I'm going to write both just to be redundant. 3.6 times 10 to the 22nd newtons. Okay, that's mostly correct, but it's not quite correct because of that too. So I'm going to write 4 times 10 to the 22nd newtons is the final answer. That's how much force is felt. That seems like an awful lot. So where did I mess up? Well. Just so right now that answer is not passing the smell test, but at least I'm consistent. So I mean, from what I could tell, that is correct. So for now, I'm just going to have to leave it like that. If I figure out why that seems, I mean, that's a ridiculous amount of force. So something's going on. Probably just one of the numbers in the I don't know. So something's wrong, but it's set up correctly, and yeah, we did it correctly. So probably one of the numbers that's given is just incorrect somehow. I don't know. But that's all there is. So I don't see any questions. And I believe that's all I have to say. Just again, go back through this. There's a couple of things to keep in mind. Make sure you're familiar with those things. Definitely make sure you have those 3 equations and 3 constants written down on your note card, and then anything else you want. And of course, just let me know if you have any questions. So not seeing any questions, I'm going to call it a night. So good luck, study hard, and I'll see you on Friday.